Okay, so the title of this set here I'll show you is Intro to Light, but I should really maybe change it to the Intro to Light and Color. Okay, so it turns out then that the color of light that comes out is very important for, say, astronomy, because if the light's blue or red or whatever, there might be some science that is to be understood. And so let's just see where color comes from. So it turns out that if I go back over here to the radiating charge, which is the source of light that we were coming from, where light comes from, you can see that as the charge goes up and down, you can see these wavelengths of light sort of traveling away. You can clearly see the crests and the valleys, and you can also think of it as a frequency going up and down, like this little part right here is going up and down. And of course, we said I can increase the frequency like this, or I can decrease the frequency like this. So it turns out that even though this particular simulation leaves the light waves in white, higher frequency waves like that would be one color, and lower frequency waves like that would be another color. And so light and color then are intimately related to the frequency and the wavelength. Those are what dictates what color light we're going to see. Okay, and so I'll also say that the higher the frequency, that tends to lead to bluer light, and the lower frequency, that tends to lead to red light. So let me just show you what I mean. So if I go to this graph here, which I sort of found on the internet, it has exactly what I'd like you to see here. So you see here that these waves here have a longer wavelength. In other words, the distance between the crests is a bit longer. And as we also learned, wavelength here, a longer wavelength is going to mean shorter frequency. So when you have sort of a longer wavelength and a shorter frequency, that's what gives red light like this. So if I went back over to the simulation here, we would generate red light using something about like this. Remember, this is a very high frequency right here, and the wavelengths are very small. This is a low frequency right here, and the wavelengths are very large. Remember, it's still true, the inverse relation between frequency and wavelength. So if I was making the charts bounce like this might be red light that comes out, because as you can tell, it has a very low frequency and a very long wavelength. Look how long these crests are that go out. So that's exactly what might be happening, say, right here. But on the other end of the spectrum is over here, where I might get a very short wavelength. Look how close these waves are together. Remember that symbol we're using for lambda for a wavelength would be something like this. I can draw, there's one part of the arm right there, and there's the other part right there. There's lambda. Here, the lambda is much smaller. See, the distance between the crests are much smaller. But of course, also we know that the shorter the wavelength here, the larger the frequency. Because remember, wavelength and frequency are inverses of one another like that. Okay, so how would I generate blue light? Well, I could go back over the generator over here and really crank up the frequency like that. So this would be like bluer light because the frequency is much higher and the distance between any two crests on the wave are much smaller. So this would be an example of blue light. So if this is a really physically correct model, all these white lines here should really be blue. So maybe I'll go hunting around for a better one for next time or something. But in either case, that's sort of what a graph like this is showing you here, that you can get different colored light depending on what frequency and or wavelength you choose. And of course, it's true also that these longer wavelengths, shorter frequencies tend to have a lower energy, and the shorter wavelength or larger frequency tend to have higher energy. So you can see the connection right here: low frequency, low energy; high frequency, high energy. So it turns out, though, that we're going to basically stop talking about frequency now, because frequency of red light can be something like 5.5 times 10 to the 15th hertz. Remember, the hertz is a times per second. And yes, I mean 15 up there. So the frequency of light like this might be 5.5. And then you'd have to put on, well, let me get rid of the point for a second here. It'd be like 5.5. Then you'd have to put on 15 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, something like this. So these numbers are just crazy here. And I'm going to try to put some commas in for you. Like, there you go, 55 something. I don't even know what this number would be, but that's how many times per second this little portion of the light wave would be going up and down. So you can see we're way, way far removed from the 1, 2, 5, or even 1,000 hertz for sound that I demonstrated to you a couple of videos ago. Light wave just humming up and down. So these numbers are very, very inconvenient. But what's more convenient, that's why we just basically stop talking about frequency now, but what is more convenient to talk about then is the wavelength of light. And that'll be much more important to us, as I'll show you on the next slide. So we're going to get away from these waves now, and we'll just look at the colors as they exist. So here we go. This is much more convenient for us in terms of talking about light. So what's down here on this axis, these are just the wavelengths. And look how nice the numbers are, 400, 450, and these are all nanometers, which are billionths. So all these wavelengths have for visible light that we see are in the billionths of meters, which are okay. We don't need to worry too much about that. But the point is that the numbers are so nice and digestible. So what we definitely need to know and identify with is that 400 nanometer light down here is associated with blue light. So when the distance between two crests of a light wave are about 400 nanometers, 400 billionths of a nanometer, our eye will perceive blue light. Likewise, when you get over here on the red, when the distance between two crests of a light wave are 700 nanometers, our eye will perceive red light. And when you get sort of in the middle right here, about 500, 550, let's just say 550 nanometers, something like that, that will be green light. So that's the better mapping then. Instead of messing with the frequency and all those just very bizarre numbers that the frequency of light can have, if we just go to the wavelength, the numbers are very digestible. So it's very important to know as we proceed with astronomy, 400 nanometers, blue light, 500, 550 nanometer, green light, red light, 700 nanometers. Those are sort of the light categorizations that we'll need sort of proceed with our discussion on light.